So in the last section of this course, we talked about lipids, and I showed on the board what lipids would look like on a two-dimensional basis. I also talked about the numerous carbons that are connected with one another, and I've talked about the fact that this structure, this long chain of carbons, is rather hydrophobic, which means that water does not interact with structures like that, basically because of the way the electrons are shared within all the atoms in a structure like this one. So what we have here is a molecule that's called palmitic acid. It is a saturated molecule, so there's 16 carbons. And then if you want to, of course, you could count them. So there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, and then 16 right here. And when we look at the structure, we see that we have between each carbon, we have this green link here, which demonstrates that there is some covalent bonding going on right here. So all those gray beads here are carbon atoms, and each of those carbon atoms are connected to hydrogen atoms as well. So if I spin this molecule in space like I can do here, then we can tell that these carbons are assembled, or the display here is like in a zigzag kind of position. And the reason for this, as I explained before, is because carbons form this tetrahedron structure, this little four-phase pyramid in space, so that whenever these atoms are connected together, they form this little jagged shape right here. Now look at every carbon here. We know that carbons have the possibility of forming 4 links with other atoms. And then if we look at, let's say, this carbon right here, let's look at this one. So what we have here is we have this carbon, and then we have the 2 links between 2 carbon atoms here, and this carbon is also connected to 2 hydrogen atoms right here, right? The last one here is CH3, so we have carbon here, and then because they're linked to 4 atoms, we have 1, 2, and 3 more atoms here. And then every single one of those carbons in the middle are CH2, 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 meaning that there is a carbon with 2 hydrogen atoms connected to that. Now, this is a structure that is a saturated molecule. And what I mean by that, and what we mean by this, when we say saturated, we mean that all the carbon atoms are connected to every single one of them share 1 link with an atom next to it, and in this case, the hydrogen atoms, right? So the thing here that you will notice is that, and we haven't looked at this yet, is that this structure is called palmitic acid. So the acid component to it is right here, and we have a carbonyl group right there. We've seen these carbonyl groups in amino acids. That's why they're called amino acids. So this is the acidic portion of it. We have a carbon here, and the red beads here are oxygen. So CO right here, and then we have an OH and hydroxyl group right here. So that's why we talk about palmitic acids. Now, from now on, when we're talking about lipids, we will talk about acidic molecules such as palmitic acid and linoleic acid and all of that. So we'll see that there is this acid part to it. Now let's not make this too complicated. Lipids are still a long stretch of carbon connected to one another, and they can be either saturated or unsaturated. Now, speaking of unsaturated lipids, we now have another kind of lipid. It's called oleic acid. And this oleic acid right here has all the carbons. There's 18 of those carbons, and I'm not going to count them here. You can count them if you wish. But we have here, and we look at this, we have carbon, 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 carbon. And the interesting thing here is that in the middle right here, we have two carbons that are connected with one another, but they are sharing two electrons instead of sharing only one electron that we see here between the carbons, right? So what we have here is a covalent bond, but it's a double covalent bond right here. So basically, because of this, and because of the fact that carbons will link to only 4 different atoms around them, or they have the possibility to form 4 bonds. What we have here is this carbon has 1, 2, 3, and 4 bonds, but 2 of those bonds is shared with the neighboring carbon atom right here. So that's what we see. Now the interesting thing here in this cis unsaturated lipid is that this connection right here creates, as I explained before, a kink in the molecule, right? So it's no longer linear like palmitic acid was previously. We now see that there is a kink, there is this space, it occupies, it's a bit more bulky in a way, right? So that is very important, because when we talked about different lipids, and when we will address the phospholipids and their roles in cell membranes, we will see that several degrees of unsaturation and cis bonding, like we see here, have a huge impact on the physiology of cell membranes. Now, speaking of molecules that have more than one unsaturation, so we say that it's polyunsaturated. So the previous molecule that we looked just before, this one was oleic acid. It was a mono unsaturated fatty acid. There was 18 carbon to it. And we say mono unsaturated because it was only one site where there was one unsaturation, so basically one double bond. Linoleic acid is polyunsaturated. It's still 18 carbons, but it's polyunsaturated. And we might not see this very well here, but let me just spin the molecule a little bit. And now we can very well see those different bonds right here, double bonds. So we have 1, 2, and 3 here. There's still 18 atoms of carbon to this, and we still have the acidic component. That's why it's called linoleic acid. But we see that this molecule now is more bulky than ever, right? It's more bulky than the other one was. One thing that I want to show here is that these bonds, in this case here, these bonds create a little bit of a more of a kink in this molecule. You can see that there is one right here, and then when you look at that, the interesting thing here is that what we have here is a kind of a cis bonding here. We have this part here, and then we have a trans bonding right here and right here. So basically it keeps the molecule kind of like a bit more linear when we compare this with the cis unsaturated site. Now let's make things a little bit more complex. What we've seen so far is only one structure of lipids. We've seen the long carbon chain, and I just recently introduced that there is the acidic component to it, so that's why we call the previous molecules palmitic acid, oleic acid, or linoleic acid. When lipids are transported in cells, they can be transported in various ways. So what we see here is something that is called a triglyceride. So what we see is all those chains right here. We have 1, 2, and 3 chains, but what you can tell is that those 3 chains are connected together. They form a bigger molecule than just the long stretches of carbon right here, right? So what we have here is that in the middle, right here, let me just position this so we can see it a little bit better. What we have here in the middle at this spot right here, we have a molecule that is called glycerol. And glycerol has a possibility to link 3 different other molecules. And in this case, we have 3 lipids connected to one another. So this is what a triglyceride would look like. Now, just to look at this a little bit, if we strip down all the distracting molecules that we had previously, we now see that we have the glycerol molecule right here in the middle, 1, 2, and 3 oxygen here. And then what we have is that if I spin this in space again, I can tell that those skeleton of fatty acids, so we have 1 here, 2 here, and the third one right here, they're all connected through this this molecule here. So we have the carbon atoms here, and we also have these oxygen atoms that are connecting to these 3 fatty acids. So this makes it a triglyceride. Now, soon enough, when we will explore the different components of a cell, we will look at the cell membrane. And we will see that the cell membrane is formed is composed of the building blocks, basically, of the cell membrane is composed of a very special type of lipid. It's called a phospholipid. So what we see here is 2 long chains of carbons. So those long chains of carbons are no different than what we've seen before, right? So they're connected in a very specific way, and we have the structure, the zigzag structure that we see here between the carbons. And remember that those chains here can be either saturated, like in these 2 cases, but it can also be unsaturated, and we can have cis or trans unsaturation. So basically, that's the way the carbons will be configured in this molecule here. But what we have on the top here is we have this molecule here that is composed of phosphorus and other atoms here. I'm not going to get into the details of this too much, but that's basically phosphoric acid right here. So and we can connect 2 chains right here. Those 2 chains can be exactly the same. They can be as long as the other one. So say we could have like a C12 and a C15, or we could have a C13 and a C13, something like that. But what I want to show and talk about here is that, remember when we talked about those long chains of carbons here and here, we know that these 2 chains are hydrophobic. So they don't interact with water too much or at all. But what's interesting here is that this part here of this lipid is charged. And because this is phosphorus, it is charged negatively. So it has a negative charge. And what's interesting here is that when we have a molecule like this, which we have a part of it that's quite hydrophobic, these parts here, and then we have a charge right here which is basically negative, we know that this part is non-polar, but this part is polar here. Hey, guess what's going to happen when water comes in the mix, right? Water is going to interact with this part here, but of course it won't interact with this part right here. So it makes this molecule quite special, because some of that molecule has affinity for water, can interact with water, while the other one cannot. So the interesting part here is that there's a name for molecules like that. And we say that if it likes, or quote unquote like water, or wants to interact with water, we say that's hydrophile, and this part right here is hydrophobe. Well, a molecule like this is amphiphile, and amphi, A-M-P-H-I, it means all around, right? So there's more than one affinity. One can interact with water, this part here, and the other one cannot. And as we will see when we talk about membranes, this has a huge impact on the structure of that membrane.